Geometry Unit 4, Section 7, Isosceles Triangle Proofs. This video is all about using the concept that isosceles triangles we know have two congruent sides and two congruent angles. And the two congruent angles are the angles opposite the congruent sides. So a phrase we're going to use in proofs when we're given an isosceles triangle is that the angles opposite congruent sides of a triangle are congruent. So angles opposite congruent sides of a triangle are congruent. So if you're given a triangle with two congruent sides, then the angles opposite those sides in the triangle are also congruent. And that's really going to be the key of what we're doing here. So let's take a look at how this will pan out in a proof. So let's set up our statement and reason table. Okay, so we're asked to prove triangle ABG, which is this triangle here, is congruent to triangle EDF, this triangle here. So we're going to look for three pairs of congruencies, and our first given is that AC is congruent to EC. AC congruent to EC. And let's put that down as our given and take a look at how we can use it and what it means. So AC. Now, triangle ABG here has a side called AB, not a side called AC. AC is this big side here. That's not the same thing as AB. So AC is a congruency, but it's not a side congruency for the triangle I'm trying to prove. Now, the first thing students often think with this is, well, it's too long, so I must have to do some subtraction. And that would be true if I knew these pieces were congruent. See, AC is congruent to CE on this side. And if I were able to cut off BC and CD, well, then I'd have AB and DE. But I can only subtract off CB and CD if I know that CB and CD are congruent to each other, and they didn't give me that information. So I don't know these pieces are congruent. I can't subtract them to get the pieces that I want. And, you know, it's possible that you could come across a proof that does involve that type of subtraction, but that's not what this is really going for. And when you're given two sides of, or two segments congruent that happen to also be segments of a triangle together, like you see how AC and CE, they are congruent, and together they form a single triangle of ACE. So they're two sides of a single triangle. And whenever you're given two sides of a single triangle congruent, it's almost always trying to hint towards the isosceles concept that we're talking about here. So the fact that AC and CE are congruent means that this whole triangle is isosceles. And if that whole triangle is isosceles, well, in an isosceles triangle, we have two congruent sides, but we also have the angles opposite those sides. And the angle opposite AC is E, and the angle opposite CE is A. So these are the angles opposite the two congruent sides of the big triangle here, ACE. And those angles are also angles of the smaller triangles I am trying to prove congruent. So when you're given sides congruent that are not your triangle sides, but sides of a different triangle, you first want to think about isosceles before you jump to any type of subtraction. And so that's what we need to use this for, is this isosceles principle that the angles opposite congruent sides of a triangle are congruent. So what we need to do is make a new statement, and we can say that angle A is congruent to angle E. And the reason is the angles opposite congruent sides of a triangle are congruent. Angles opposite the congruent sides of a triangle are congruent. And it's because it's an isosceles triangle. Do I have to say the angles opposite the congruent sides of an isosceles triangle are congruent? No, because if they're congruent sides, that implies that it's either isosceles. It could also be equilateral, and the angles opposite the three sides of an equilateral are also congruent. All three of those angles, because they're all 60 degrees. So it's not limited to just isosceles, but that tends to be when we see this, because usually we're not trying to solve three angles, congruent. We have two angles are congruent here. So that's really it for the new piece there. That's what that given does for us. Let's take a look at the next given. AF is congruent to EG. And the rest of this is a normal looking proof. Nothing new here, just stuff that we've been doing. But take a look at AF. And maybe we haven't seen this yet. AF. That, again, is not a side of my triangle. My triangle has AB, AG, BG. It doesn't have AF. AF is too long. Well, we've seen a couple of times now when you're given a segment that's too short, you need to do addition. Well, when you give a segment that's too long, you need to do subtraction. And that's what's going to happen here. But didn't we have something too long last time, with our first given? Yes, but like I said, I can't subtract with that first given unless I know this is congruent to this, and I don't know that. But I can subtract down here because I do know what I'm cutting off from both sides is congruent because it's reflexive. There's the difference. I can't subtract up here without knowing this congruent to this, and you don't. But you can subtract down here because you do know GF is congruent to GF. And so we have to do that. So the subtraction process is very similar to the addition process. It's just subtraction instead. So often it requires reflexive, not always, but it does require reflexive. Now this proof could have been written differently. Like the given information. Maybe they did if they gave us that these were congruent, then I would have done subtraction and gotten A, B, and D, E. But like I said, we have to use what they give us. So this is a reflexive property, and then we could do subtraction. And it always lines up to AF minus GF, EG minus GF. So AF, sloppy F, minus GF is congruent to EG minus GF. And the difference of these, what is AF minus GF? It is AG. And EG minus GF is EF. And AG and FE or EF, those are sides of the triangles I'm trying to prove congruent. So that is a side congruence right there. So it's time to take a look at what's going on our next given here. Lastly, you're given angle ABG. Switch colors to black. Angle ABG is congruent to angle EDF. That's given information. I just realized I never wrote subtraction up here. And so where are those angles? ABG, that's up here. And EDF is up here. That's an angle congruence of your triangles. You don't need to do anything with that. So we got an angle congruence from the angles opposite congruent sides of a triangle are congruent from the isosceles there. And then we got a side congruence through subtraction. And then we were given another angle congruence. And all of that together are three congruencies that I can use to prove my triangle is congruent. So let me state that my triangle, and I want to use ABG, is congruent to my other triangle, EDF, because I have two angle congruencies and at one side congruency. The side congruency is not between the angle congruencies, therefore it is angle, angle, side is congruent to angle, angle, side. All right, so that's it for how an isosceles triangle, if that type of thing is given to you. And it might not say isosceles triangle. There's no mention of isosceles triangle here. We were just given a congruency here that we have to realize that creates an isosceles triangle, which creates angles opposite congruent sides. And so you have to kind of watch out for that. But that is the type of thing we'll see, and we'll practice more of that in class. See ya.